Human impact on the nitrogen cycle is diverse. Agricultural and industrial nitrogen N inputs to the environment currently exceed inputs from natural N fixation. As a consequence of anthropogenic inputs, the global nitrogen cycle, Fig. 1, has been significantly altered over the past century. Global atmospheric nitrous oxide, N2O, mole fractions have increased from a pre-industrial value of approximately 270 nmol per mole to approximately 319 nmol per mole in 2005. Human activities account for over one-third of N2O emissions, most of which are due to the agricultural sector. This article is intended to give a brief review of the history of anthropogenic N inputs and reported impacts of nitrogen inputs on selected terrestrial and aquatic ecosystems. History of anthropogenic nitrogen inputs. Approximately 78% of Earth's atmosphere is N gas, N2, which is an inert compound and biologically unavailable to most organisms. In order to be utilized in most biological processes, N2 must be converted to reactive Nh, which includes inorganic reduced forms, NH3 and NH4+, inorganic oxidized forms, NO, NO2, HNO3, N2O, and NO3-, and organic compounds, urea, amines, and proteins. N2 has a strong triple bond, and so a significant amount of energy. 226 kilocalories mol 1 is required to convert N2 to Nh. Prior to industrial processes, the only sources of such energy were solar radiation and electrical discharges. Utilizing a large amount of metabolic energy and the enzyme nitrogenase, some bacteria and cyanobacteria convert atmospheric N2 to NH3, a process known as biological nitrogen fixation, BNF. The anthropogenic analog to BNF is the Haber-Bosch process, in which fossil fuel H2 is reacted with atmospheric N2 at high temperatures and pressures to produce NH3. Lastly, N2 is converted to NO by energy from lightning, which is negligible in current temperate ecosystems, or by fossil fuel combustion. Until 1850, natural BNF cultivation induced BNF, e.g., planting of leguminous crops, and incorporated organic matter were the only sources of N for agricultural production. Near the turn of the century, Nh from guano and sodium nitrate deposits was harvested and exported from the arid Pacific Islands and South American deserts. By the late 1920s, early industrial processes, albeit inefficient, were commonly used to produce NH3, due to the efforts of Fritz Haber and Carl Bosch. The Haber-Bosch process became the largest source of nitrogenous fertilizer after the 1950s, and replaced BNF as the dominant source of NH3 production. From 1890 to 1990, anthropogenically created Nh increased almost ninefold. During this time, mango population more than tripled, partly due to increased food production. Since the Industrial Revolution, an additional source of anthropogenic N input has been fossil fuel combustion, which is used to generate energy, e.g., to power automobiles. During combustion of fossil fuels, high temperatures and pressures provide energy to produce NO from N2 oxidation. Additionally, when fossil fuel is extracted and burned, fossil N may become reactive, i.e., Nox emissions. During the 1970s, scientists began to recognize that N inputs were accumulating in the environment and affecting ecosystem functioning. Impacts of anthropogenic inputs on the nitrogen cycle. Between 1600 and 1990, global reactive nitrogen Nh creation had increased nearly 50%. During this period, Atmospheric emissions of near species reportedly increased 250%, and deposition to marine and terrestrial ecosystems increased over 200%. Additionally, there was a reported fourfold increase in riverine dissolved inorganic influxes to coasts. Nitrogen is a critical limiting nutrient in many systems, including forests, wetlands, and coastal and marine ecosystems. Therefore, this change in emissions and distribution of Nh has resulted in substantial consequences for aquatic and terrestrial ecosystems. Atmosphere. Atmospheric N inputs mainly include oxides of N, Nox, ammonia, NH3, and nitrous oxide, N2O, from aquatic and terrestrial ecosystems, and NOx from fossil fuel and biomass combustion. In agro-ecosystems, fertilizer application has increased microbial nitrification, aerobic process in which microorganisms oxidize ammonium, NH4+, to nitrate, NO3, and denitrification, anaerobic process in which microorganisms reduce NO3- to atmospheric nitrogen gas, N2. Both processes naturally leak nitric oxide, NO, and nitrous oxide, N2O, to the atmosphere. Of particular concern is N2O, which has an average atmospheric lifetime of 114 to 120 years, and is 300 times more effective than CO2 as a greenhouse gas. NOx produced by industrial processes, automobiles and agricultural fertilization, and NH3 emitted from soils, i.e., as an additional byproduct of nitrification, and livestock operations are transported to downwind ecosystems, influencing N cycling and nutrient losses. 6 major effects of Nox and Nh3 emissions have been cited. 1. Decreased atmospheric visibility due to ammonium aerosols, fine particulate matter, PM. 2. Elevated ozone concentrations. 3. Ozone and PM affects human health, e.g., respiratory diseases, cancer. 4. Increases in radiative forcing and global climate change. 5. Decreased agricultural productivity due to ozone deposition. And 6. Ecosystem acidification and eutrophication. Biosphere. Terrestrial and aquatic ecosystems receive Nh inputs from the atmosphere through wet and dry deposition. Atmospheric Nh species can be deposited to ecosystems in precipitation, e.g., NO